Welcome to our class exercise on random samples and Monte Carlo methods. In this video, we'll simulate rolling the dice to get numbers between 1 and 99 and plugging those numbers into the spreadsheet to generate log normal values using the frequency factor method, which is shown here on the slide. So for each individual number, xi is equal to the average plus the standard deviation times the random number variate, which is in a normal distribution. All right, let's go. In this video, we will demonstrate how random sampling works by using statistics from real highway runoff data. The data is from 50 events sampled by Kirk Smith in USGS Water Resources Investigation Report 02-4059. In class, we use two 10-sided dice to generate uniform random integers between 0 and 100, effectively 1 to 99. We convert these to percentiles, calculate normal variates by using Excel's norm.sinv function, and use the frequency factor method with Kirk's statistics to build a population of suspended sediment data. In this demonstration video, we will use Google's online generator at https:/g.co/kgs/adsqes as our virtual dice because it generates a value with each click. We will enter values in column B under roll values. When we enter roll values, we see the individual concentration and statistics evolve. The cumulative average values and percent difference from Kirk's 289 milligrams per liter are shown on the graphs. Ignore graph values beyond your roll number. Now let's generate some random concentrations. On the Google tool, click Generate to roll the dice. Enter each value in column B, the roll value cells. As you enter each value, the statistics will be updated and the graph will show the results of each entered value. Click the tool again to get a new roll. Okay, we are at 10 samples and our average is 388.9, about 35% higher than the known average. We are at 20 samples with an average of 374, which is 29% above the known average. There are at 30 samples. The average of 314 is about 9% above 289. For 40 samples, we are at 301, only 4% above 289. Samples, we are at about 298. This is about 3% above the real average of 289. We got within and stayed within 10% at 30 samples. Let's copy this tab and try rolling the dice again to see what would have happened in a parallel universe. Now, let's generate a new population of values. In this universe, we are at 205 after 10 samples, which is about 29% below Kirk's 50 sample average of 289. At 20 samples, we are at 232, which is about 20% lower than 289. After 30 samples, we are at 256, which is 11% below 289. After 40 samples, we are at 254, which is about 12% lower than 289. After 50 samples, we are at 263, which is 9% below Kirk's average of 289 milligrams per liter. In the previous example, we ended with an average of 298, which was about 3% above the real average of 289. In that example, we were overestimating the average, and in this one, we were underestimating the average just based on the luck of our dice rolls. If we look at multiple runs, we can see that we start to converge at about 15 samples, but more samples improve the estimate. People making decisions on too few samples may be mistaken. They may not know what they think they know. Hopefully you enjoyed this class exercise.